Hi, in this lecture I will be talking about Cartesian vectors. We've talked about 2D, meaning x and y, Cartesian vectors. And remember, Cartesian vectors or Cartesian notations were the vectors and notation that we used that included I and j. Now what we are doing, we are going to discuss 3D Cartesian vectors, meaning vectors that are in real life. They are 3D. They happen in x, y, and z axis. So I want to explain two things before we start talking about components and Cartesian vectors. The first thing is the axis that we are using. They're following something called right-hand rule. And this is the relation of x, y, and z. It doesn't matter how you rotate your x and y and z, their relation to each other remains fixed and remains the same. And that is, you put axis y on your arm or forearm, you curl your fingers like that, and this is the direction of x, and your thumb is pointing to z-axis, meaning this will be wrong, because if I put my forearm on y-axis, my thumb is pointing to x and my fingers are pointing towards z, or the curling direction is towards z, and that does not make sense. So this is not a right hand axis. This is just for you to help you when you want to label your axis. You kind of quickly look at x, y, z and remember which direction each is pointing. The other thing I want to mention is Cartesian unit vectors. Remember, vector has a magnitude and direction. Magnitude, direction. Magnitude is right here, which is 1. Direction is here, which is x, y, and z. If they point to positive x, we put a positive next to them. But remember, this is also a Cartesian unit vector. Let me put ijk, because books sometimes use bold letter to show vectors. This is minus I, positive z, negative x. So this is going to be minus k. This is positive y. This is minus y. So this vector is going to be minus j. So remember, x, y, and z, I, j, and k. Okay. So now let's look at a vector in a 3D space or a Cartesian vector. So the goal is to either have ax, ay, az and find a, or start with a, find ax, ay, and az. So the goal is basically to express a into its component. So same as before, I'm going to write vector a is a resultant of its components, ax, ay, az. Okay, remember, this is a vector and all of these are vectors, and so on. If I want to use Cartesian notation, one side is a vector, so the other side needs to be vector too. But look what I'm doing. I will use the magnitude of ax. One side is a vector, this side is a magnitude. What is missing? A direction. How can I add direction to a sub x? By using unit vectors. So I put a unit vector next to it because it has a magnitude of 1, so it only, as if it only has direction. This whole thing now is a vector. So now it is correct. So I'm going to do the same thing, and I'm going to do the same thing for z. Okay, so this is called Cartesian notation. Remember, whenever we use I, J, K, that is a Cartesian notation. So if you remember, in a 2D x and y, I had fx, I had fy. The magnitude of f, do you recall? How did I find it? It was x squared, or sorry, fx squared plus fy squared. So let's see, how can I do the same here? Okay. So let's find magnitude of a prime. Do you see where a prime is? Something like this. It has a x and a y. Okay. Ax and ay, the goal is just like before, that I found f. The goal is to find this a prime magnitude. So similar to up here, if it was only an x and a y, which is exactly here, it's just x and a y, it's just laying flat. Magnitude of a would have been ax squared plus ay squared. Again, this is magnitude. Okay, so we established magnitude of a prime. So now let's look at this triangle here, or this parallelogram right here. This is a prime, this is 90 degrees, and this is my vector a. So let's look at it. This is an observant. Look at it from this side. I'm just going to draw it flat. Okay, this is a prime, this is that 90 degree, this is my a. And let's see, what is this length here? Is AZ, which is the same length as here, AZ. So if I want to find, so this is my XY plane and this is my Z axis. So again, it's a 2D now. Again, look up here. How did I find magnitude of f? It was fx squared plus fy squared. Here, how can I find magnitude of a? Is a prime squared plus az squared. Okay, I've already found a prime. So a prime squared is ax squared plus ay squared. All I have to do is replace it there. Ax, ay, az. So if you have the three components, before if we had two components, fx and fy, we could find a magnitude, right? See the similarity? All we've added to it is a third term, which is that az squared. Okay. If you recall, for 2D, we had two different ways of showing the direction, right? One was angle with one of the axes, doesn't matter, x, y. The second way was something called slope triangle, meaning just giving a triangle right here, whatever, 3, 4, 5, to show the slope. For 3D, also we have two cases. One is using coordinate direction angles. In other words, angle that our vector, in this case a, makes with each x, y, z axis positive direction. I could have worded better. So coordinate direction angles are the angles that A makes with positive x, with positive y, and positive z axis. So let's look here. The blue vector is my vector A, and it is making an angle alpha with axis x. I don't know if you can see it. It's right here. Making an angle beta with y-axis, with, I should say, positive, an angle gamma with positive z-axis. So let me see, I might have to, yes. So let me clear this here. Okay. Here is a little bit better and more clear explanation. Okay. First of all, let me see. Is my y, z, and x, they've kind of rotated, right? But let's put it to the right hand test. Y was supposed to be in the direction of forearm. So that's my forearm. Z was supposed to be in the direction of my thumb. And X was supposed to be in the direction of the way you curl the fingers. Sorry, it's not the most beautiful hand. So, yeah, Z, X, and Y. Yes, so that is right hand rule and it's working, okay? So although it's rotated, it's still right hand rule, so we can still use the axis. So let me clear that one as well. Okay. But now look, the angle that A makes with positive x-axis, theta of x, which we like to call it alpha. The angle that A makes with positive y-axis, which we like to call it beta. And the angle that A makes with positive z-axis, which we like to call it gamma. Now, I'm actually glad that I used a different example because the axes are rotated, so you can see that it doesn't matter which way it's laying. It's always with x-axis we call it alpha, with y-axis we call it beta, with z-axis we call it gamma. Okay, so let's not forget the goal. The goal is to find AX, the magnitude of these, AY, and AZ from vector A. So let's look at the blue shaded triangle. I know it kind of looks weird. But this angle is right here is 90. So if I draw it, kind of looks like this. This is my A. This is my AX. And that is by that 90 degree. And the angle that this makes is alpha. Okay? So let's see. So my cosine alpha is what in this triangle? Is AX over A. Again, these are magnitude. These are all magnitude. Okay, let's look at this tan color shaded triangle. This one. Right, this one. And I'm going to draw that one also in a flat way. So this is my A. Okay, this is the 90, and this is my AY. The angle between A and axis Y, which is this, is called beta. Beta has just like a little tail at the end of it. Cosine beta is AY over A. Okay, and last, let's look at this light green shaded triangle. And I'm going to draw that one as well. Draw it flat. Kind of like that. This is the 90 degree. And This is my A. Right here is AZ. The angle that it makes is gamma. Cosine gamma is AZ over A. Okay, so I think we're getting somewhere. Remember, the goal was to find these three. So all I have to do is rearrange my equation. AX is A cosine alpha. AY is A cosine beta. AZ is A cosine gamma. And if I want to write it in Cartesian notation, remember, A is AX, AY, AZ. They're all vectors. I can say, use magnitudes. Now this is magnitude. I, magnitude J, magnitude K. These are all the same. It just, I'm only using different notations to show them. Or, based on what I just learned, I can just say A cosine alpha I, A cosine beta J, A cosine gamma K. So these are the three ways that you can show vector A and its components. Okay, so let's look a little bit deeper here. I just told you that A equals A cosine alpha I, A cosine beta J, A cosine gamma K. Okay, let's divide both sides of this equation by magnitude of A. Okay, so one thing that I can see right away is this A and this A, this A and this A and this A and this A. Okay, so now I want you to think, what happens when you divide a vector by its own magnitude? Just think about it. You're not messing with direction at all. You're just dividing it by its own magnitude. So in other words, if this A was whatever, 325 newtons, and you divide by its own magnitude of 325 newtons, what would you get? A magnitude of 1. The direction is still the same. So, do you know what we call a vector with a magnitude of 1 in a certain direction? Yes, you're right. We call that unit vector. So by dividing any vector by its own magnitude, I get unit vector of A, meaning a vector with a magnitude of 1 in the direction of A. Now this is getting interesting. So I have a unit vector equals cosine alpha I, cosine beta J, cosine gamma K. What is magnitude of a unit vector? You're right, it's 1. What is magnitude of any vector? Let's see, A, 1, I, 2, J, 3, K. Magnitude of A, remember, was number 1, whatever it is. It's not number 1, it's whatever goes in that place. Right? So magnitude of U is cosine alpha, cosine beta, cosine gamma, all squared, In other words, cosine squared beta cosine square gamma equal 1. So what I did here is just prove that this relation exists between the 3 coordinate direction angles. And what that means is, if someone gives you 2 of those, 2 of the angles with axis, you can find the third one and go back, put it in this equation, and find the magnitudes. I promise it's going to be a lot more clear when I do and go over some examples. All right, so this was option 1, meaning you have a vector and you have the coordinate direction angles. You have every angle that that vector makes with every axis. What if you don't have that? And you have a case kind of like this. So let's first test, quickly make sure that this is a fits right hand rule. Put your arm against Y, your fingers should be X, your thumb should be pointing to Z. Okay, that makes sense. So this is right hand, so I can use IJK and my normal cosine alpha beta gamma. But here I have angle with Y axis, right? But I don't have angle with X axis or Z axis. So I don't have coordinate direction angles. What I have is called azimuth and transverse angle. But what I like to call it in my classes, I like to call this a shadow method. Okay, I'll explain to you why. All you have to do in these cases, so the goal is to find, again, goal is to find AY, AX, and AZ. So let's see. If I look in this triangle, well, this is not A, sorry, this is F. I didn't see the F here. So this is F, this is B, or no, sorry, F, Y, and this angle is theta Y. So cosine of theta Y is going to be Fy over F. Okay, so I found one of them. Fy is F cosine theta Y. The next thing I got to do is I have to find a shadow. So let me write this here because I have images for you. Cosine theta. Okay, so if I want to find shadow of F, so I have a light source coming in here. Okay, that vector F is going to make a shadow on X and Z. So can you guys tell me what is the magnitude of F H here? Magnitude of the shadow. Let me draw it. If an observant look from here, it will look like this. This is Z axis, this is F, and this is theta Y. I am interested in this magnitude, FH. Can you tell me what is FH? Now you got to think 2D. Sine of theta y is what? Is FH over F, right? Do you agree? Because FH, sine of theta y. So magnitude of FH is F sine theta y. Okay? Let's not lose focus. What we're trying to find is Fx, still missing. Fy, I found it right there. Fx and Fz are still missing, and I'm trying to find those. So now, again, we put an observant there. Let's look at it 2D. I have Fx, I have Fz, this is z-axis, this is x-axis, and I have an FH and an angle phi. My Fx is going to be FH cosine phi, and my Fy is going to be, Fz is going to be FH sine phi. Good thing I already found my FH. So I'm going to replace this instead of FH here. F sine theta y cosine phi, and my Fz, F sine theta y cosine phi. So to make it, like, summarize it and simplify it, if you have coordinate direction angles, meaning if you have alpha, beta, gamma, the angle that A makes with every single axis, then you can simply put it in this equation, which is A cosine alpha, A cosine beta, and A cosine gamma, and find the components. But if you don't have angle with every single axis, you have one of them but not the other two, so you have to do a two-step. Step one, find shadow, okay, which is right here that I found. Step two, transfer that shadow to the axis that you're looking. Here it was x and z axis. In next video, I will go over numerous examples that uses either the transverse and azimuth angle, or use coordinate direction angle to find the components of a Cartesian vectors. Thank you for watching.